Hello, we're going to go through the class notes for 6.1, and this is going to discuss the periodic table. But before we get to the periodic table, we need to understand that these elements had to be organized into this type of structure. And that started with scientists and chemists as they started to see patterns of characteristics with different elements. And initially, those patterns were kind of grouped into what we call triads. And it was only with Dmitry Mendeleev that we started to see some sort of a table grouping. So let's talk about Mendeleev. In about 1869, Mendeleev arranged the elements that were known at that time by increasing atomic mass. They didn't know about subatomic particles. They didn't know about protons, neutrons, and electrons, so there was not another way to organize. This was his initial method of putting the elements into some sort of structure. So what Mendeleev did is the elements that had similar properties, he put in the same group, or what we call column. Okay, the columns and the groups, sometimes called families, on our periodic table are going to be arranged. For example, this is group number 1. Okay, that is a column. Group number 2 is the next column over. Mendeleev left some gaps because there were some undiscovered elements that were later discovered. He actually predicted properties of these elements and did so pretty successfully. And so there was some affirmation when the elements were discovered and their properties were described to see that Mendeleev had actually predicted these correctly. In this method of using atomic mass to order the elements, that meant that the two elements, tellurium and iodine, seemed like they were out of order. And that is because tellurium has a greater atomic mass than the element that follows it, iodine. And we now know that's because of the isotopes of tellurium with greater numbers of neutrons. But it kind of stumped Mendeleev, and he thought maybe the numbers were wrong. So after Mendeleev put together his periodic table and he was, the gaps were starting to be filled in, it was only later that Henry Moseley actually reconfigured the periodic table based not on atomic mass, which is what Mendeleev did, but based on atomic number. Now, the reason that Mendeleev could do that is that subatomic particles had been discovered at that point. In fact, we know from the gold foil experiment that Rutherford was the scientist attributed with discovering protons, but it was Moseley who assigned atomic numbers, which again, that's the number of protons, to each of the elements and arranged the periodic table by increasing atomic number. That was a really important understanding because our current periodic table starts with element number 1, hydrogen, and then goes to element number 2, helium, and increases by number of protons, which is this atomic number, until we get to the number of protons for the largest element, which at this case is 118 protons. Okay. This solved the tellurium iodine problem because even though tellurium has a greater mass than iodine, so we would have expected using increasing atomic mass to have these switch. Tellurium has atomic number 52, whereas iodine has atomic number 53, so it follows, and that puts them correctly into their space in the periodic table. All right, next up, let's talk about what this means for some of the different types of elements that we have, and this idea of periodic law. Okay, so for periodic law, you have a definition from the book, but really what that's saying is that we have properties that repeat, that put elements into a particular column. Okay? And our elements, we can divide into some very large categories. Let's look back at our big periodic table here. And you'll notice that not only on your smaller periodic table, Plainsman periodic table, but on the large one here, that there's a dark line that we call the stair-step line. Goes like stair steps here. Okay, that dark line is really important in separating the major types of elements. Anything that is to the left of that line is an element, or sorry, is a metal, okay? Obviously an element. So these are all metals. There is an exception to that, okay? So besides the F block, all of the D block, this half of the P block, and the S block, hydrogen is actually not considered a metal. So hydrogen, even though it's on the left side of that stair-step line, is considered a non-metal, okay? So now let's look at the stair-step line again and consider the elements that are to the right side of that. The elements to the right side of the stair-step line, you can see that's quite a lot fewer, not as many as the metals. These are called non-metals, okay? Any elements that are touching the stair-step line may be a metalloid. So there are a couple of exceptions there. Aluminum, even though it's touching the stair-step line, is considered a true metal, okay? But others that are touching the stair-step line would be considered metalloids. So metals, non-metals, and then metalloids would be touching the stair-step line, okay? So let's talk about characteristics and what puts those elements as those different types of things. So for metals, make a note in your notes that this is the majority of elements. So about 80% of all elements are metals. The defining characteristic for metals is that they're good conductors of electricity. And we're going to do a lab coming up here in the next week or so where we look at characteristics of metals and non-metals and metalloids by testing different substances. And those that conduct electricity and conduct electricity well are our metals. Okay? There are other characteristics. So I have something right here that says other properties. We'll look at the fact that metals tend to be shiny. There'll be varying types of colors, but most metals will be kind of a silver gray color. And that they will tend to be malleable, which means they can be bent or pounded into sheets. And of course, that defining characteristic of being good conductors of electricity. Metals are also good conductors of heat, but the good conductor of electricity is our defining characteristic. So now let's look at non-metals. In your book, they said that for non-metals, these tend to be poor conductors of electricity and heat. I would like you to cross out poor and put this in instead. They don't conduct electricity, okay? Non-metals can conduct heat, but in terms of a defining characteristic, I want you to write this. Non-metals don't conduct electricity. Now, as far as other properties for non-metals, we'll find that there are varying types of things because non-metals is a lot of different stuff, all the different types of things that can be non-metals. So as far as the state that they might be at room temperature, non-metals could be solids, they could be liquids, they could be gas, depending on what that particular element is. Whereas metals at room temperature tend to be solids. The only exception to that is mercury, which is a liquid at room temperature. So for non-metals, they can be solids or liquids or gases. They tend to be dull, as in not shiny, whereas metals are shiny typically. And they tend to be brittle, which means that they'll break instead of bending, okay? And of course, they don't conduct electricity. Now there's the third type of element, which is metalloids. And metalloids are kind of unusual. Those are those ones that are touching the stair-step line. So along the stair-step line here, oops, here. And metalloids have properties of both metals and non-metals. Please never tell us that metalloids are a mixture. They are not. They have characteristics of both metals and non-metals. So they might be shiny, but brittle, or they might be dull like a non-metal, and maybe somewhat malleable. So they're going to have some mixture of characteristics, but they are in no way a mixture of metals and non-metals. Their characteristics have some of each of the different major categories, metals and non-metals. Sometimes we call these semiconductors, and that's because there can be some conductive character for metalloids, especially if they are, if if we work with them in terms of either temperature or filling in some gaps with some other types of atoms. Okay, so that's our 6.1 class notes. I hope you got those written down.